All right, let's talk real quick about half-life then. So half-life for first-order reactions are fairly easy to calculate. They're easy to calculate for a first-order reaction because since it's first order, that means you only have essentially one reactant that the rate is dependent upon. Since this is not dependent upon more than one reactant, so two different concentrations, it's very easy to calculate then and look at the difference in the rates over time. So what half-life is the time it takes for the concentration of the reactant to decrease by half. So what's important to note is since the line is exponential, since it's going down at a curved rate like this, that means that the half-life doesn't mean there's just two of them. Okay, so if we start, let's just throw some numbers on here. Let's say we start with 100 grams. Okay, the half-life, one half-life would be the time it takes it to get down to 50 grams. So the initial thought is, okay, if this right here, if this first amount of time, let's say it's 3 seconds. That means after 3 seconds, half of it disappears. Well, after the next 3 seconds, the other half will disappear. But that's not the case. If another 3 seconds goes by, it's going to decrease by another half, but it's going to decrease by half to become 25 grams. So divided by 4 from the original. Then if another 3 seconds goes by, it's going to divide by another half, and so that would be 12.5 grams. And this will keep going on, in theory, indefinitely, dividing by 2. But obviously, once you get down to one molecule, it's going to decompose, and you'll be left with nothing. So the half-life is the time, and it'll change. So this number, this 3 seconds that I threw out of this 100 grams, it can change depending upon the molecule. So it could be really long half-life. Some molecules, we talk about this a lot with nuclear, with radioactive materials. So some half-lives are thousands of years, millions of years. Other ones are just a few seconds. So this might occur really quickly or might occur very, very slowly. And obviously the rate also changes with temperature. And so that means the half-life is also going to be dependent upon the temperature of the molecule or the temperature of the reaction. But overall, just the general term is the half-life is the time it takes for the concentration to decrease by half. And you'll notice that the time is always the same for it to decrease by half. So even as the concentration decreases, the half-life will stay the same. Here's another little pictorial. So this is showing the concentration versus time. So initially we started out with a bunch, and then after a certain amount of time we were left with half of what we started with. And then after another same amount of time, okay, so time, this one it does it in minutes. So after 1 minute, half of it had decayed or half of it had reacted. After another minute, half of that had reacted, so a quarter of the initial amount. And after another minute, this in half. And then after another minute, we would be down to 1. Then after another minute, we would be down to 0. Let's take a look at a practice problem. So we've got a reaction here with N2O5 dinitrogen pentoxide, and it is reacting to form nitrogen dioxide and oxygen gas. And we can see that it is a first-order reaction. How do we know this is a first-order reaction? It's because we have a natural log of a concentration, and we wind up with a straight-line graph when we graph it against time. So that should be a clear sign to us by now that this is a first-order reaction. So let's find the half-life for this reaction. So the first thing we're going to want to do is take a look at the integrated rate law for a first-order reaction. And that would be negative kT equals the natural log of the concentration of, in this case, N2O5 after a certain amount of time minus natural log of the concentration of N2O5 initially. And since we're looking for the time, the half-life is a time. So let's rearrange this equation and solve for time instead. So that means that time is equal to the natural log of the concentration of N2O5 at time. It's the natural log of the concentration of N2O5 initially divided by the negative of K. So what we can see from this is we're going to need to get that K value before we can solve for the half-life. So the K, remember, that's just the slope, or the negative of the slope, and we can find the slope from our graph pretty easily. So our rise would be from negative 0.493 up to negative 3.91, and our time, our run, would be from 600 to 0. And so we can find out our slope then pretty easily, and we would find it to be 1.7 times 10 to the negative third, and then the units of that would be seconds inverse again. And so now that we have that K, remember that K stands strong for any point in this concentration, so we can plug it in up there. So let's think about this half-life thing. The values we're given on our data table are already in natural log, so we can go back and convert them into regular form if we want to plug into this right here, or we can use them as they are. But there's actually a better way to do this. So the half-life, we call it the T half, would be equal to the natural log of the concentration at a particular time minus the natural log of the concentration initially. So I'm leaving those blank for a reason, and then our K value is 1.7 times 10 to the negative third seconds inverse. So take a look at this. Let's say, just for example, that our initial concentration is 1. How can you do that, Jones? 1 isn't on our graph at all. Remember, that K value, that slope, stands true for any of this reaction at this particular temperature. So we could throw any numbers in there we want. And so if we're starting with 1, after a single half-life goes by, so after the time of one half-life goes by, how much would be left? If you said 0.5, you are absolutely correct, because after a half-life, half of it is gone. And so we're left with half of it. So we can just solve this equation just like this. Don't really need to pick any numbers off the data table. Don't even need to do any fancy math to figure out what our initial and final concentrations are. Just start at 1, end at half. That's a great way to always do these half-life problems. So then if we solve this, we would find that the half-life, the time for half of the dinitrogen pentoxide to decay, is 408. What are the units on this? Well, that's molarity right there, that's molarity right there, and remember, a log minus a log is really the same as a log divided by a log, so those would cancel out. We're left with seconds, so that means the units of this would be seconds. So, dinitrogen pentoxide decays by half every 408 seconds. So if we started with 1, we'd wind up with 0.5 after 408 seconds. After another 408 seconds, we'd be at 0.25, and it'd keep going on until all of it had decayed into nitrogen dioxide and oxygen. So this equation, this half-life equation, is not given to you on the AP test sheet, but it's pretty easy to derive. If you just remember the 1 to 0.5, that's all you have to do. And in fact, there's actually a simpler way to write this even than that. So let's just use a generalized equation again. So the A changing into B. Okay, it's a first order reaction. So that means the time of the half-life would be equal to the natural log of the concentration of A after a certain amount of time minus the natural log of the concentration of A initially divided by the K value. And this would all be a negative. So if we think of it again as 1 and 0.5 instead up here, let's plug those in, call this 1 molar and 0.5 molar. Oops. We can do that because it's half-life, so it's the time it takes it to decay by half. So we're starting with 1, ending with 0.5. We have those numbers in there. We don't even have a reaction. We don't have time shown in here. Let's figure out what those are. So our time half-life would be the natural log of 0.5, and the natural log of 0.5 is negative 0.693 minus the natural log of 1, which is 0. And we would divide that by our K value. And so look at this. We've got, the negative from the equation and the negative right there. We've got a 0 right there. So we can simplify this half-life equation for a first-order reaction as T half equals 0.693 divided by K. Keep in mind this equation is not given to you on the AP test. It is a very simplified version of the half-life equation. All we're saying here is the half-life for any first-order equation, this only applies to first order, would be 0.693 divided by its reaction constant, or its constant. Okay, not given to you on the test, but if you can remember that, it'll come in very handy. If you can't remember it, it's really easy to derive. 1 and 0.5 plugged into the integrated rate law.